All right, let's get started. Today's colloquium is by Tom Woods. Tom is a scientist at LASP. Actually, Tom is an associate director at LASP. Tom got his got a bachelor's in science from Southwestern University in Memphis in 1981. And 4 years later, his PhD from Johns Hopkins University. Tom mostly works on solar UV radiation and its impacts on the Earth's atmosphere. And today he's going to be talking to us a little bit about a CubeSat and perhaps some other satellite missions that he's involved in. Tom?
All right. Well, thank you. I guess I need to turn this on. Hello? Testing? Works? Okay. Well, thank you for the invitation to come talk to you about CubeSats and what we've done recently with the NASA CubeSat to actually do science. Obviously, the box is the CubeSat. And the little peeps up there, since we're getting close to Easter, you know, you get those for Easter all the time. We've decided, you know, our student-run operations center is costing us, you know, a few $1,000s a year. We think if we can go to the peak-type ground station, we can get the cost down even lower. But anyway, just a silly picture I found. This is a shoebox diorama, and I'm going to show you a shoebox next. So this is almost exactly the size of a 6U CubeSat, a shoebox size. I'll define a U in a minute, but the MinX is only 3U, so we can fit 2 MinXs in this shoebox. But I only have one here. If I can get it out. This is not a flight unit. This is just a little prototype that the students have put together. I'll be talking about MinX a little bit. It has all the same ingredients of a regular satellite. I'll talk about this in a few minutes and demonstrate it. But this is the size a CubeSat called for a 3U. It was, you know, originally started, the concept was started in 1999 as an educational tool at Stanford. Let's give the students something to build that could go into space. It took a few years before they got the first CubeSat launched in 2003. And then later, NASA started doing technology demonstration. They didn't think you could do science with CubeSats. They thought you could just prove small technology. So they had their first technology CubeSat launch in 2006. And then, as many of you probably know, Teresa started the NSF Geoscience CubeSat program to do science, educate students and do science. And their program started in 2008. First launch was 2010. And then Congress decided NASA should be doing science CubeSats. So Congress mandated NASA to do CubeSats for science. NASA did not want to do science CubeSats. They thought CubeSats were just going to be a lot of orbit debris. It's just going to be junk up there. None of them are going to work. They don't want to do them. Well, Congress decided in 2014 that thou shall do science CubeSats. So MinX is the first one to launch, and we are doing science. It's not just debris up there. They've actually selected about 24 science CubeSats that will be launching over the next couple of years. So science from CubeSats, I think, is about to explode. You may have been familiar with the NRC report. I was on one of the panel members talking about what science you could do from CubeSats. So that is maybe also another motivation to do more science from CubeSats. If you were at the Boulder Solar Day yesterday, you probably heard Amir's talk. So some of this will be overlapping with Amir's talk about the MinX CubeSat that we've been operating the last year. We built 3 units. We have the prototype, which is sitting here. Flight Model 1 is up in space now, taking data, and Flight Model 2 is supposed to launch later this year into Sun-sync orbit and at higher altitude, so we'll get about another 5-year mission off of that. Primarily, the science team here with Stan Solomon here at HAO, who's helping us with understanding not only the solar variability, but also how does it affect the ionosphere and thermosphere. And of course, we got lots of students. I'll introduce some of them here in a little bit. First of all, I think most of you know what a CubeSat is. It's considered a unit is basically 10 centimeters cube. Technically, it's not exactly 10 centimeters cube. It's really like 10 by 10 by 12. But it's standardized size, so that makes it easy to design for. You don't have to just be, you're confined by space. So it helps actually, especially for students, to think inside the box. They can't just design anything. They have to fit this size. If they can't fit the size, then, well, do something else. It is scalable in the sense that you can launch 1U, 2U, 1.5U, 6U, 12U. They even have a 27U dispenser. And that's the other nice thing. It's the satellites all launched in a dispenser, all encapsulated in the dispenser. So if your CubeSat's not very well made and it falls apart while being launched, it's all captured. So it's not going to hit the primary satellite or hurt anybody else. It may come out in pieces when it gets ejected, but as far as I know, that's only happened once or twice.
So, is there any rationale for that size? You said, defined by these people. Is there a argument for coming up with those size?
I'm not sure why they started with the 10 square centimeter or cube size. It's just like, what science can you do in something small? Of course, at that time, it was just what technology could you fly at the time. Of course, what used to be considered a standard satellite was 1U, about the size of a grapefruit. Then they started flying 3Us like this. And now 6U, the size of the shoebox, wherever that is, that's now the standard for NASA to pick. I do think the 12U will be the next. I mean, the more bigger, the better for science, right? So I'm not sure why the U got defined as it is, but it does help confine the design. And that surprisingly is an important factor for getting something built quickly is not having it open-ended. We don't fly red hard parts, we just fly commercial parts, and I'll talk about that in a little bit. So these are relatively inexpensive. NSF CubeSats were capped at like $900K. MinX was only about $1 million, mainly because we'd already built most of it after 2 years in a student class in the aerospace class for 2 years. Typically, you can propose to NASA like $4 to $6 million for a 6U CubeSat. And I'll talk about some of the technology about why you can do that. As far as the number of CubeSats launched, as of February, there's 614 CubeSats. Can you guess the name of the company that's launched half of those? Planet Labs. So the little 3U imager, kind of competing with Google for imaging the globe. They launched like 88 in February at one time. So they've launched over 300 of these. And it's a commercial business. It's not even for science. It's just commercial business. They're going to sell their images to people. They just bought up a Google satellite program called Terabella in January. So they're going to launch bigger satellites too that Google was building up, and we're actually launching MinX 2 on this Terabella launch this fall. So we're getting a free launch from Google, which is now Planet. So they're definitely the leaders. Now, as far as debris, do you know how many items are in space that is bigger than 10 square centimeters? There's over 30,000 items they're tracking. So out of space debris, what's a few hundred, right? So that was one of the interesting things when we did this NRC report was the first thing people came in is like, CubeSats are horrible. They're just going to cause too much debris. You can launch 100 in a year. That's much more debris. And it's like, yeah, but it's 100 out of 30,000 already. Is that really that much more debris than necessary? Because a lot of times you have satellites colliding and creating thousands of parts. So yeah, it's a concern, but it's not as big a concern as some people make it out to be. As I mentioned, CubeSats are a tool for education. They were generated to help train students. They didn't really care if the satellites worked or not. And that's still true for technology satellites or educational satellites. They just want to train students. But what I'm focusing on, of course, is the science aspect of CubeSats. NSF, as you're probably aware of, kind of started the science CubeSat programs. Here's the ones they selected. The one they selected from CU called Colorado Student Space Weather Experiment. Chillian Lee and Scott Palo led that program, and it was a very successful 2-year program before the battery died. And then in NASA, MinX is one of the ones in heliphysics, and here's all the listings here of the ones selected for space science. And it's over all 4 divisions. Believe it or not, they're even trying to do astrophysics. We last got one selected just a couple months ago in astrophysics with Kevin Francis, the PI, to study Alpha Centauri and look for planets around one star. So this little 6U CubeSat is just going to stare at Alpha Centauri and just look for planets for a year. So even astrophysics, where you think you need large apertures, can do science. MinX was built as a student project. Every semester we'd have about 25 students. Here's one example of the class. But one of the important things that lessons learned, at least from LASP, is you don't just turn students loose. You give them a lot of mentoring. Just like professionals make mistakes, students make mistakes too. Typically when you lay out a printed circuit board, even professional engineers will lay it out 2 or 3 times before they get it right. Well, students maybe 4 times instead of 3 times. But they do finally get it right, and you do have quality products, and it does really matter to have a professional relationship with them. Here's all the people that actually touched MinX satellite. I didn't believe this list when I first saw it. There's 80 people there. Half of them are students, half are professionals. And typically when we build a big professional satellite, especially instrument, there'll be 80 people working on that too. So even though it's a small satellite, a lot of people actually worked on it. And the motivation for MinX is solar motivated to study the soft X-ray region. If you were here yesterday, Amir talked about how there's a gap in this part of the solar spectrum. This is energy going down to higher energy, or wavelength going up. Here in the soft X-rays, there's the SDO measurements and RESI measurements, but there's soft X-ray. We have broadband measurements like from GOES XRS, but not really Spectra. And as I'll show you in a few minutes, there's problems with understanding these broadband measurements, and this is MinX is solving that problem. So I'm going to switch to technology for a little bit. Why can we do the science on CubeSats today versus 10 years ago? Well, obviously, it's a technology. Some of the innovations we have on MinX include a commercial instrument. We didn't have to build the instrument. We just bought the instrument. We did take it apart and conformal code everything so it can survive space environment, but you know, typically an instrument for space costs $1 million. This is a $10,000 instrument we just bought. Another one is pointing. 2 years ago, you could not point a CubeSat to better than a few degrees, but a small company here in Boulder called Blue Canyon Technologies developed for the Air Force an attitude control system that's 1/2 U to point with better than 10 arc seconds. And we're seeing 8 arc second quality pointing from this system. Our source satellite that measures the solar radiance program for the last 15 years, it's only getting about 10 arc second pointing too. I mean, this is as good as a full-size satellite pointing. The other thing that we students did, we made 3D printed parts. Generally, they're not as strong as if you take a full chunk of metal and machine it out, but we allow the students to experiment, and they did some 3D printed parts, some hinges out of stainless steel and some housings out of aluminum. And then the other thing I've already mentioned is low cost electronics. Now the key for electronics to survive in space is they gotta at least be red hard to some level. Of course, depending on your orbit, you need different levels of red hardness. We found that automobile parts, high-grade automobile parts that can go over wide temperature ranges, they typically test out to survive space at 10 to 25 K reds. So the little MinX that we launched first from the space station only need 2 K reds. So this is way overqualified even for that. Now the SunSync orbit for MinX 2 is about 20 K red. So we do need harder parts for that. And we tested all our stuff and they passed 25 K red test. So even these cheap, inexpensive parts, we believe will survive space for about 5 years in SunSync orbit.
kind of a naive question on the launch. What kind of G's these things get? That's not an issue for most of these things?
They're typically 10 Gs. Now we do our vibration test on everything to verify they're going to survive. So you could have problems of commercial instruments not being, qualified to meet that. Of course, you should test that before you launch so that if it does break, you can fix it and stuff. But yeah, it's about 10 to 15 Gs depending on the launch vehicle, which isn't that harsh really. But the two key technologies that made MinX successful, one is the X-ray spectrometer. It's, as you can see, it's handheld size. We buy it from Amtech for about $10,000. It only takes about 2 watts after it warms up. It takes 5 watts to cool down the detector. So that whole unit here, that little end point here, about the size of your thumb, includes a thermoelectric cooler, a vacuum vessel, the detector, op amp, everything the size of your thumb. That's the science. Now, rest of the electronics, going the wrong way. Rest of the electronics here is electronics to take that signal and to partition all the photon events into a spectrum. So it's just digital electronics, but it's amazing what you can buy on even for instrument these days. So we run the detector about minus 50 degrees Celsius to cool it down so we get really low noise. And that's worked extremely well in space. The other one I already mentioned is the 1/2 U attitude control system. It's also about 2 watts, and it's given us about 8 arc-second pointing. So there's 2 requirements of any attitude control system. You got to have a safe mode. As soon as you launch, you got to find the sun and point at the sun so your batteries don't die. So that's our safe mode here. Their design was within 10, it would find the sun within 10 degrees. It doesn't use a star tracker or anything else. It just has a coarse sun sensor and it goes to the sun. So it's doing better than 10 degrees. It's doing about 3 degrees. And then you send a command and say, go to find precision pointing. Then it starts using the star tracker to get very precision information where its attitude is in space. And it's getting about 8 arc seconds. There are, because we're only flying one star tracker, there are points when the Earth occultates the star tracker and it has to do a roll maneuver, and you can see it deviating away from that. Basically, the RMS noise on here is about 8 arc seconds for each axis. Now, this was early in the flight. You can zero this out to be 0 if you want, but early in the flight, this is the demonstration of 8 arc second pointing. You can buy from Blue Canyon 2 star trackers, so you don't have to have this roll effect every orbit. I'm going to talk a little bit about the design. I already mentioned to some degree the science goal is to measure the solar soft X-rays and to study flares from it. Here's a typical example of many flares per day from GOES X-rays. Again, those are broadband measurements, but we've seen over 100 C-class flares so far on our mission. And thanks to this weekend, we've doubled our M-class flares. There were 7 M-class flares this weekend. So we've got a lot of new flares to study now on MinX. Unfortunately, we're still downloading that data, so I'm not going to show you any data from that. I'll show you data from, there's another big burst in July of last year where we had about 8 M-class flares. I'll show you some of those spectra. Our biggest limitation is data. We only have about 500 kilobytes per day downlink because we 9600 baud. You can overcome that with the S-band or X-band radios, but we just went with the ham radio type radio that's 9600 baud. What's really nice about UHF, it's ham radio equipment. Everybody has it. The whole ground station costs $10,000 to install. It's just really inexpensive equipment. So this is kind of the same thing as you see here. Basically, we have all these electronics that just slide in, plugs into a motherboard. You have the instruments down here, and we have the attitude control system up here. Typical size board is about 3 inches by 3 inches. And we got basically 4 boards plus the attitude control system. And just like any big satellite, just like any baby would have, they have all the same organs as the adult. So The small CubeSat has the same components as a big satellite. I call them the 4 Ps. You've got your power, you got your processor, you got your pointing, and you got your phone, your radio. You can also add a couple more Ps if you want, propulsion, payload. We don't have any propulsion on Minx, but all the same components you put in a big satellite. And the students built pretty much everything but the attitude control system. We bought that, and we bought the instrument. It's primarily what we bought. And the students built everything else. I already talked a little bit about the instruments. Another instrument we flew that's broadband to help calibrate the X123 is a GOES-R instrument that the students repackaged. So it uses red hard parts and stuff, but it was donated to us from NOAA. Attitude control system I already talked about. Typical, again, processor boards about 3 inches by 3 inches. We store all our data on SD card. We buffer all the data. We can't downlink all the data because there are communication downlink issues, but we can collect on the SD card like a year worth of mission. So we go back and decide what we want later. So even if we don't get the data down this week, we can go back 3 months later and say, oh yeah, we missed this flare. Let's download that data. So SD cards are definitely much bigger than they used to be. So you can store a lot of data on them now. One of the innovations the students did was instead of stacking electronics, which makes it really hard to test and integrate, they made a motherboard design so you can slide the cards in and out. It also helped with thermal control where each board is mounted to a thermal rail here, and this outsides here then are coated with silver Teflon tape so that these can radiate out the heat. So they also had to do thermal design for this to help keep the temperatures reasonable. Electrical system, basically power converters. We got lithium polymers batteries that are from up the road here at SparkFun. Extremely good batteries. We've had some of these batteries sitting around on the shelf to see if the voltage changes, because one of the problems with CubeSats is you don't get any electrical interface before you launch. So you deliver like 3 months before you launch. They sit there for a long time with no power to them. The batteries could be dead when you launch. We've had these batteries sitting on the shelf for over 2 years, and they've kept their charge. So if you ever need the part number for these turned out to be like the world's premier battery, and we didn't do anything but pay like 20 bucks for them. We got lucky probably. But anyway, the students build up a battery pack, test them, and get them ready for launch. And they built their own solar panels. Basically, they built the printed circuit boards. They buy the solar cells. So these are space qualified triple junction cells, just like a big satellite would fly. We buy them from Azure Space in Germany just because it's the right format for a CubeSat. They built 3D hinges here made out of stainless steel so that they're spring loaded. So these solar panels basically are on a spring. You have a fishing line to hold them down. Fishing line goes over a resistor. You heat up the resistor, it pops open. Very, very simple, reliable ejection system. One of the interesting things we've discovered in building these solar panels up, if you put the reverse voltage on the cells, they glow bright red. So you can see where there's any imperfections in the cells. So you could test your cells, throw out the bad ones, and put new ones on. Anyone knew that you could run solar cells backwards and see them glow red? Well, yeah, it's bright red. At least the triple junction cells. But I guess the silicon, so it's probably the silicon making it red. Anyway, that's a great way to test solar cells without having to. It's a 5-minute test. We did buy the radio from Lithium One Radio, so that was another item that's purchased. And then there's antenna deployment. So the antenna deployment, again, is the fishing line deployment system. It's a very simple system. Basically, again, there's a fishing line. It opens up, and it's a measuring tape. Now, the measuring tape has to be precisely the right length to give you the right frequency. So the big science experiment for the students was to take it in an RF chamber and keep cutting it off until you got to the right frequency. But that's been very reliable and pretty standard in CubeSat technology for simple radio. Now the fishing line and the resistor It's also a very simple release mechanism, but it's a little bit more specific research than you'd think would go into it. One is it can't be just the high-end fishing line. It has to be the cheapest nylon fishing line. And the reason is if your resistor doesn't melt the fishing line, if you take nylon fishing line, it's sensitive to UV solar radiation. It will melt in about a month in space. So that's your backup system. If you don't open up, then hopefully it'll be sitting in the sun long enough, it'll just degrade the nylon and it'll break open. The other one is, of course, picking a resistor that will actually heat up. You know, you got to get the right power ratio. If you get it the wrong ratio, then it actually will blow up the resistor. And students blew up plenty of resistors finding the right resistor. Or vice versa, if it's not enough power, then it won't heat up enough to melt nylon. So it actually turned out to be a bigger research project than I thought. But after going through about 40 different resistors, not only the technology, but just different selections, they finally found the resistor that's been extremely reliable. So even the little things can get you. The structures is all aluminum. They pretty much designed and built that themselves. We did have a machine shop build the final flight versions because we built 3 copies of them. And then, unlike when we deliver a satellite for LASP, we typically will do what we call the white glove delivery from FedEx, where they bring in a truck dedicated to you. It's all air conditioned and everything. And you load up an 18-wheeler with all your equipment and you haul off to some NASA center to do your integration. For this little CubeSat, it's one static case and one box of tools, and all that we just carried on the plane with us and delivered it to NanoRacks down in Texas, where there's actually a 6U dispenser. So the Michigan Cadre satellite was in one half of it, and our little Minx CubeSat's in the other half. And then they launched in December 2015. It took several months before they released us on the space station. We thought we were going to be released in January of 16, but apparently the Japanese arm has to grab these NanoRack modules, take them out of the airlock, and then point them down and shoot these CubeSats off. Apparently the Japanese had one and the US had one, and they fought for 5 months who would go first. In 2 days, they could have launched everything. It was a little bit frustrating to watch them argue week after week. Who's going first? Who's going first? I think it went up to the president level. Anyway, they finally launched this in May. And so this is the Japanese arm. You can barely see it, holding the NanoRacks. And this is Cadre came out last. We came out first. And Amir showed, I think, the movie yesterday. Basically aim it down so that it doesn't come back and hit the space station on the next orbit. And here's a team that was there for commissioning the instruments. And unlike a NASA satellite that takes a couple months to commission, we had a commissioning plan to commission this in 2 days. We have our own ground station, own antenna, Yagi antenna on the roof of LASP. And we even, because it's ham radio, any ham radio operator can grab our packets and send it to us. So we're beaconing data all the time. And we've got a whole network of international ham radio operators that just send us packets every day. Now, it's not as much as we can do with a single dedicated ground station, but it's really nice to get packets from anywhere. And they seem to like doing it. We're not paying them. But we did have one problem. The radio did not like to listen. It was sending data just fine. It took us a couple days to find out the radio needed more power. Our ground station needed more power. So we had to up our 100-watt power amp to a 500-watt power amp, and we haven't had any problems since. But we were scared there the first couple days because it wasn't accepting commands very reliably. And after we got this big power amp, it's been very reliable. Okay, any questions about the technology before I move to science?
Just as briefly, are you able to do most of this testing, the rad testing and stuff at LASP? Or how much are you having to go out?
So we don't do rad testing. We send them off to, there's several places around the country that do rad testing, but we don't do it at LASP. We do like thermal vacuum testing we do at LASP, vibration testing. There's several places in town like Ball where we can go do vibration tests. We're not required to do any EMI or EMC electromagnetic, interference type testing, although there's facilities in town to do that too. But yes, we do functional testing. One of our engineers, Rick Koner, actually built an air bearing table because this is the first time we're flying the Blue Canyon ADCS. Will it really point to the sun, or the standard classical problem, or you add a phase and it goes away from the sun? So he built an air bearing table. He basically took a bowling ball, made a shell of it, then polished it, and so it was really smooth. And he had two halves of the bowling ball basically, so one half fits in the other and flow air in it. So he had a air bearing table. So we mounted this on top of the air bearing table, and we have a helostat at LASP, so we just pointed the sun down there, and sure enough, you point it off 45 degrees, whoop, lock onto the sun. So we proved that it was going to point at the sun before we launched it, which isn't just another test. I mean, the key to any satellite, regardless if it's CubeSat or real satellite or any real experiment, balloon experiments, ground experiment, is testing. And I think that's probably the most important thing of having successful instruments, that you test it thoroughly before you deploy it. And that's been something LASP has been doing for decades. I've been on NASA projects where I get in the crunch, and it's like, oh, we got to make this launch date. Let's give up some testing. It's like, that's the last thing you want to do. Delay the launch if you have to, but don't give up testing, because you find all sorts of things. You can design and design and design and design, but little things like timing conflicts or many other little things like that will creep up on you in a test. So, any other questions on technology? Okay, a little bit on the science. So we have 3 science objectives. One is to understand the coronal heating processes, both quiet sun as well as active regions, looking how that's evolving. Now, over a solar cycle, we can't really do that with MinX-1 because it's only a 1-year mission, but with MinX-2, we'll have basically a combined 6-year mission. And I'll be talking about how we look at this heating process in a minute. The second one is studying flare energetics, which is very much related to question 1, just in a different time scale, really. And then question 3, which is where we rely on Stan Solomon and his GCM modeling efforts, is to understand this solar variability that we're measuring. How does it really impact the ionosphere? And his focus is primarily on the E region dynamics, which is the least understood part of the ionosphere. Or at least he tells me that's the least understood part. Maybe Young has a different opinion. And we have team members to help with the modeling, both differential mission measure models as other models as well, and looking at the flare temperatures and abundances, and also looking at Phil Chamberlain's FISM proxy model, making that better as well. Mainly because we don't have measurements in this, spectral measurements in this range. We've had proxies for the solar soft X-ray spectra for decades, so this will hopefully now provide real measurements for those. Amir showed this yesterday. This is just an example of our problem with broadbands. Most of our broadbands measure 0 to 7 nanometers. We do not know what this spectrum looks like. I mean, you can theoretically use Chianti and guess what the spectrum might look like. But this is 2 spectra that has exactly the same irradiance. We don't know which spectrum we measure broadband, which this spectrum is. And if you put this, of course, into the Earth's atmosphere, you get different altitudes and different depths and different amount of heating at different wavelengths, quite dramatically different. Stan has done some model runs. This is from his AGU talk last December, where he used some of our MinX spectra from the July flares, looking at how the E region and D region enhancements are from this M5 flare, and looking both at the glow models, whereas the time GCM, the energy deposition. We've got a lot more to do in this area to probably make more scientific discoveries, but this is the first run of the model for that. And one of our motivations, of course, is flares. If you look at Chianti spectra, and this was been recognized for a long time, but if you look at a Chianti spectrum, right around 2 nanometers, you get a huge enhancement in irradiance. And there's a gap here where no one's measuring in this. We think, before we launch MinX, that on a large X-class flare that this got brighter than Lyman alpha, just based on modeling it. So this was one of our motivations. Let's actually measure this spectrum and see where these hot coronal lines really are. This is also the hardest part for the Chianti spectral model because there's so many hot ions and they don't have all the atomic lines in the Chianti model. They've of course made improvements every year, but we're also motivated to understand the spectra better. And as most of you are quite aware, in the hard X-rays you get a lot of impulsive heating when you start a flare. In soft X-rays it's usually smoother. In the EUV you can get both impulsive and the gradual phase smoother component. And as you probably well know, the Warren-Newport effect, if you integrate the hard X-rays or the microwave thermal emissions, you can predict the soft X-rays, and that's been part of the FISM model. So part of this is now measuring this spectrum to help the FISM model understand this more accurately. The soft X-ray spectrum is very easy to understand. Plasma parameters, especially corona plasma parameters of temperature and abundance. It's got lots of lines, but you can see here as a function of temperature, this is just Chianti model at different temperatures, how dramatic the radiance changes. I mean, we're changing at, say, one wavelength. You can change by orders of magnitude just by changing the temperature by a little bit. One of the techniques is using differential emission measure, where you estimate basically the emission measure and the temperature, and this is a model based from Harry Warren, not on MinX, but on EUV data from SDO, showing kind of typically what a flare D&M might be, and I'm going to show you something similar from MinX. The other important thing is, as I mentioned, related to corona heating, is what's the source of the plasma in the corona. So many of you are probably very aware of the first ionization potential, the FIP effect, where the plasma in the corona is typically, relative to the photosphere abundance, is typically a factor of 2 to 4 more. You see this in the solar wind, you see it in coronal loops, but if you look at open magnetic fields where plasma is coming up from below, spickles, fast solar wind from coronal holes, those tend to have more, the abundance of more closer to the photosphere, factors of about 0.5 to 1. So we know these different mechanisms relate to different heating. Nanoflaring is an example where you can get low FIP effects in the coronal loops. But the challenge has been, over the past 10 years, there's papers all over the board talking about, well, what about flares? Some flares have high FIP effects and some don't. Why? And we're starting to make progress on that. I'll show you some spectra first and mention the progress. But so here's a typical example spectrum. This is Hinode XRT image of the flaring of this M5 flare. Actually, I think a C6 flare in June. And pre-flare spectrum is shown here in green. The black is the flare spectrum, and all these different emission lines, iron, calcium, silicon, those are all low FIP sensitive abundances. So we can measure the intensity of these emission lines to get abundance ratio very easily. We've looked at, of course, as I mentioned, especially July period, we've gotten several M-class flares in just a 1 week period, and hundreds of C-class flares as well. The red is the GOES XRS data. The green is our spectra integrated. No, I'm sorry, not integrated over XRS. This is just total signal, but it's basically showing you the variability there. And then a similar type comparison of the spectra. And you can see a very different, as this is in energy. So as this gets harder in energy, that means it's a hotter temperature. We're typically fitting at least a 2 temperature component instead of a full D&M at this point, but we can also working on D&M modeling to get more temperature. But basically you can get the temperature very easily, and then from these different emission lines you can get the abundance very quickly. Here's an example of a 2 temperature fit component where, and it's not just really 2 temperatures, it's really a Gaussian distribution over temperature. The pre-flare is shown here in green, and black is the fit for 2 temperatures for the flare spectrum. And you can see it's very similar. This spectral shape here of this is very similar to what Harry Warren had from looking at EUV flare D&M. So I'm going to compare now what we get from MinX, comparing to what GOES has been giving us for decades. So the technique, one of the techniques you can use on GOES broadband measurements, you can take the ratio of the XRS-A to B long wavelength and short wavelength X-ray, and this ratio, you look up the ratio and you can look up a temperature. So people have been using for decades the ratio of XRS-A and B to get a flare temperature. And another technique is the same in the EUV, where you take a ratio of 2 lines, you can get a flare, for example. So I'm going to show you the comparison of what we get with MinX. So red is the GOES technique, where you just take the ratio of 2 lines. With MinX, we can fit multiple temperatures. The green is the MinX fit, and you can see it agrees quite reasonably well with the GOES XRS, but we also get a cooler temperature that's comparable to the pre-flare temperature. The other thing that we don't get from XRS is the abundance. So doing this flare anyway, the abundance went from corona down to photospheric, which means there's a lot of heating in the photosphere. Standard flare model where you have magnetic reconnection to corona, you get a lot of energetic electrons and protons both going up and down. The one's going down, heating up the chromosphere, the photosphere, that heats up, evaporates up, and you get all this new plasma into the coronal loops that have photospheric type abundance. So we're seeing this on eruptive flight type flares. What we're not seeing this go down is on compact flares, where the magnetic reconnection is just in the coronal loop and it's not really heating stuff below. So we're not ready to write a paper about it, but we're definitely studying the difference between when you get the abundance changes and not. We do see both cases of flares, and we think the differences between eruptive flare and compact flare. But stay tuned. We may learn more. We got more flares this weekend. So here's the temperature that I showed you for just a few flares. This is over the whole mission. And you can see that it agrees fairly well with GOES at the high end of the flares. But as you get to the low end, one, it bottoms out, which surprises me. But it bottoms out about 2 million Kelvin. The GOES, because it has a background problem, it can't actually get down to low enough radiance, so it has a floor here. So we know this is bogus temperatures from GOES at the lower radiance levels, but the black representing here, we believe, is the real measurements of the temperature. Now, these are soft X-rays. Doesn't mean you can't have a 1,000,000 degree corona from other emissions, but from the soft X-rays, it seems to bottom out about 2 million degrees. We've also looked at active regions. Here's an example from a student working last summer as an RU program, looking at, from a day-to-day, looking at how is the sun composed of quiet sun, corona hole, and active region. So basically 3 simple components, and using Chianti modeling. And pretty much in the X-rays, I don't know if you can see all these lines, the only one that really matters in X-rays is what's your fraction of disk covered by active region. It's order of magnitude brighter than everything else. So I think that's pretty well known about the soft X-rays. You just have to look at active region to get at least the total radiance out. And then the other motivation to address the soft X-ray broadband issues, we've been fighting this issue for years on timed STO source, where we got these broadband measurements in the soft X-rays, and they agreed quite well at solar minimum. The actual measurements are the green and the black, and that they differ by a factor of 3 when this is solar variability. And we think that's because of the way people are processing the data differently. In the case of the green, we're processing with a spectrum that changes every minute based on estimates of the GOES X-rays to get kind of Chianti spectra. The black, USC is processing the ESP data with just one constant spectrum throughout the whole mission. And we think that's the source of the issue. And MinX is answering that yes, that is the source of the issue. Basically, that's a factor of 3 difference in variability just because of how you're processing the data. What do you assume for the solar spectrum? You can't really interpret broadband data unless you assume a solar spectrum. And we believe that's the source. And MinX is now solving that. So here's an example, same issue with GOES calibration. How well is the GOES irradiance calibrated to? It was assumed, if you're familiar with the GOES data, you divide the GOES-B by 0.7 and you should be closer to true irradiance. You divide A by 0.9 and you should be close to the true irradiance. So this is divided by 7. And there are differences depending if it's flaring or not flaring, but it's a reasonably good calibration. If you took this over the whole mission, you find that our calibrated instrument, which was calibrated at NIST to 10% accuracy, agrees reasonably well with GOES XRS if you make that 0.7 correction, but it doesn't agree very well at the low intensities. And we've actually provided a calibration for NOAA they plan to implement next month for the GOES program. And basically, the green line is a new calibration for their XRS-B channel. It agrees with their old calibration, which is just one constant value divided by 0.7. But we see as you go to lower irradiance levels, you need a very large correction to get the right irradiance level. So we are helping with calibrations as well as science. And our MinX2 effort, we're planning to launch now in October. It was supposed to launch this month, but they've had some delays at Google, partially because Planet just bought Google. Hey. And being a longer mission, we've taken the opportunity to improve MinX2. We've got a better detector. Amtech came out with a much improved detector that has a 10-time factor improvement in linearity, so we'll be able to look at larger flares. It also has lower noise, so we can look at a higher energy resolution and longer wavelengths. We've taken a lot, we've learned from this first mission and changed some of the flight software to make it better. And to get more data back, we're adding a ground station at Fairbanks. Because of the sun-sync orbit, you get 3 times more data in the sun-sync orbit with a polar station than you can get, say, here at Boulder. So we're going to get about 4 times more data down with MinX2 per day than we are with MinX1. The prospects over solar activity, obviously we're going down toward minimum. There's still a lot to study. Even if we don't see a lot of flares, we do want to study things like active region evolution and the modeling of the effects in the Earth's atmosphere as well. And as I mentioned, there was several M-class flares that went off this weekend that we're downloading the data and looking forward to analyzing that data too. So thank you for your attention.
All right, we have time for some questions. We already had a few questions, but any more?
Yeah, Tom, for the student participating in those CubeSat, are they mostly just engineering students? Do you have a science major student?
So we ran the first 2 years of this program as an aerospace graduate student design class for CubeSat. So most of them are engineers. They, study like electrical engineering or mechanical engineering, aerospace engineering. But we do get a few scientists involved, science students involved. Those are the ones that tend to stay on. So after the first 2 years, we actually hired 4 students to stay on. One of those was a science student, and James Mason got his PhD using MinX. He graduated last April before we launched, so he did more mission design part of his dissertation. But yeah, we do get science students as well as engineering students.
How much would it be to upgrade your transmitter from this 9600 baud? I know it's very cheap, but it seems like if you're data limited, you might go with it.
So our next CubeSat we're launching is called Compact Sim that Eric Richard presented yesterday here at Boulder Solar Day. It's 6U, and we're putting a UHF for commands, but we're putting S-band down. We're going to add a 4.3 meter dish on our roof at LASP, so we're going to have megabits per second downlink for it. So we're going to significantly increase the data link.
And roughly, what's the cost differential? Is that $100,000? A couple $250,000?
Yeah, so these UHF antenna or radios cost about $5,000 to $50,000, depending who you buy it from. The S bands tend to cost more like $50,000 to $100,000. So they're not too much more expensive. It's the ground station that's the cost. I mean, the ground station is not a $10,000 ground station. It's a $500,000 ground station.
Just an idea I had at the Boulder Solar Day yesterday. related to telemetry. All these CubeSats come back to the Earth. Anyone ever thought of designing something that the data storage survives?
You would have to, that's actually a good idea. You would have to put it in something like a tungsten housing so that it wouldn't melt. Everything else is going to melt before you get it down. You would have to also have some kind of beacon on it so when it landed, you'd have some chance of finding
exactly.
it. So that's not totally out of the question. One of our weird stories, when the shuttle accident happened, we had an instrument on it, and it sprayed debris all over Texas, and people were turning in all the parts. They found the SD card of our instrument. So we actually, even though the case had melted, the electronics survived, so we were able to solder in the wires. We actually were able to pull off all our instrument data from that mission. So.
So I don't remember what the longest wavelengths were, but the characteristic temperature of the corona at those longer wavelengths, I mean, you expect to see those, what would those temperatures be as you go into minimum?
So
you sampling, was it 1.7 million?
We've seen pretty much minimum levels during the MinX mission. So this is XRS-B. It typically never gets below this level. And we're seeing temperatures with the soft X-rays. It looks like it bottoms out. It doesn't look like it keeps going down. It looks like it rolls off here a little bit. And that's about 2 million. Now I know other corona missions, they see stuff, cooler, like 1 million. But at least in the soft X-rays, that range of sensitivity is really sensitive to 2 million and hotter. Different emissions have different sensitivity to temperature. This is definitely on the hotter end of the corona. And of course, up to, tens of millions of degrees easily with soft X-ray.
Without the cheap labor from students, how much it will cost? The engineers do this.
So we're also proposing about 6 CubeSats a year from LASP without students. It's typically about a $6 million cost. And the way we do it is you can not only buy the attitude control system from Blue Canyon, you can buy the entire spacecraft bus in 1U. On a 6U, that means you can concentrate on the instrument for 5U for the rest of that money. So most of our proposals have been in the $4 to $6 million, depending on how complex the instrument is. So UHO should be looking at opportunities. What could you put in a 5U, buy the 500K bus from Blue Canyon, NASA will provide the launch for you. What could you do for like 5.5 million in 5U, and you could have a viable CubeSat mission yourself.
Anyone else?
Just wonder if you had a comment on launching the second MinX, which is a later searching mission just as we hit our solar minimum. Is there you're just doing that because now you're funded to do it? I mean,
yeah, we are funded to do this, but we had hoped that the MinX 1 and 2 would overlap so we can cross-calibrate it. Unfortunately, it's not going to happen. MinX 1 started at the space station about 420 kilometers, is now at 310 kilometers. It's predicted to enter into the atmosphere or burn up in late May this year. So we were going to launch MinX 2 in January this year, and then it was April. Now it's October, so we're unfortunately not going to overlap. But both instruments are calibrated at NIST to the same accuracy. We'll still be able to at least compare, maybe not as accurately. Of course, in the soft X-rays, it changes by a factor of 1,000, so 10% calibration is probably good enough.
Well, thanks, Tom.